Thank you. That's all right.
All right, good afternoon, everybody. I appreciate you sticking around. I'm not sure if anybody else just arrived today, but I came in from the US this morning, so I'm really thankful for Australia's coffee at the moment, allowing me to be with you all. And so my name is Zach Van Tol. I'm a third-year PhD student at Arizona State University in Phoenix, Arizona. And my background in research is I'm really interested in more of the qualitative questions, so social science and looking at homelessness and heat exposures in urban climates. So if anybody's interested in talking about that, I would love to connect throughout the week. What I'm here to do today is present actually on a paper that some of my colleagues have published in Nature Communications. So this QR code, if it works, should take you to the publication. And I had the pleasure of coming on late in the project to do some follow-up work with the city of Phoenix, investigating cool pavements and reflective pavements in the city of Phoenix, Arizona, and their effectiveness in sort of getting a better idea about the do's and don'ts of implicating this type of technology in heat mitigation. And so obviously we're all familiar with the problems of urban overheating, thinking about humans and our exposure to high heat and what that can do to our bodies, but then also thinking about the urban environment, energy usage, water usage, and environmental justice. And why I say that is I think that this is applicable probably across the world, but particularly in the United States. Urban development is a real issue, thinking about social policies and historical policies that have essentially segregated our cities. And Phoenix is really a key example of this, in which we have a city that's developed inequitably depending on the social class that you belong to in our country. And so Southern Phoenix is sort of notorious for being socioeconomically left behind, whereas some of the more affluent communities are located to the north of the city, and they receive access to shade, access to green spaces. And so this is something that we're trying to address, and I don't think it's just a problem that's specific to Phoenix, but applicable to cities across the world. So a little bit of background for those who are not from the Phoenix area or have not visited. It's a pretty expansive city. So the footprint is roughly 1,350 square kilometers, but obviously growing by the day. I was actually out in the western half of the city a few days ago, and it's crazy, the urban sprawl that is just slowly migrating further and further into the natural periphery. And out of that, I think most mind-boggling is out of that expansive size, more than a third is actually asphalt, whether we're thinking about parking lots or roadways. So that's a lot of impervious surface area exposed to summer heat, big sun, big sky. And so we have about 299 days, almost 300 days of sunshine per year in a hot desert climate. So that's a lot of incoming solar radiation for a lot of asphalt to absorb all of that energy. Average temperatures in Phoenix are above 40 degrees Celsius during the summer. And we do have a monsoon season, supposedly. I've lived there for this is my third summer, and it really is hit or miss in terms of actual monsoon weather that we experience and when that kicks in. But typically between June 15th and September 30th, we can expect more humidity and hopefully some storms, although we only average about 10 rainy days per year. And so why is this research pertinent? You might have seen global headlines about the summer heat wave we experienced in Phoenix this year, in which we had temperatures above 43 degrees Celsius, 110 degrees Fahrenheit for a full month. So the month of July, we did not have a day in which our high temperatures did not exceed 110 degrees Fahrenheit, which is pretty abnormal. Our previous record was 19 days straight of this type of weather, so we crushed that this year. And so we sort of know why heat mitigation is important, as I've already alluded to, with roadways and high thermal capacities. And when thinking about this paper and reflective pavements, trees and other shade structures have limitations when we're thinking about highway systems or neighborhoods, right? There's only certain places you can put them. And even more so to that, in a city like Phoenix, water is a major concern. So thinking about how do we weigh the costs and benefits of implementing things like trees and other shade structures. Although reflective coatings on roadways do have some limitations, which I'll get into a little bit later, thinking about the reflectivity and what that means for people who might occupy those spaces. But because of their high reflectance across solar radiation spectrum, we're able to reflect some of that incoming solar radiation and not allow it to be absorbed as heat and add to city temperatures once the sun goes down. So hopefully, as one of the previous speakers talked about, we can reduce those nighttime temperatures, which are so keen for human health. So traditional pavements typically have about a 5% reflectivity, and as they age, that actually increases. Whereas the reflective pavements that I'm talking about that the city of Phoenix implemented, they start at about 30 to 35% reflectivity, and they will slowly degrade. So they actually kind of flip-flop one another. In 2020, when the study took place, there was about 58 kilometers of reflective pavement covered, but to date, that's actually up to about 180 kilometers of roadway. So they're quickly expanding the amount of roadways in which they're covering. So here's some pictures just to kind of show you the application. It's typically sprayed on and then squeegeed and allowed to dry. And so it basically looks like what you imagine maybe your sidewalks being. And these are just some live pictures of them installing the coating on top of the pavement that's already laid down across the city. So the paper had really two main objectives. The first one is to measure air temperature, mean radiant temperature, and surface temperature, and compare that between traditional and reflective pavements. And then think about how does the surface change over the time period after it's installed, thinking about the longevity of this project and whether or not it's economically feasible for cities to be installing it. So for the study, we examined mean radiant temperature, air temperature, and surface temperature using a myriad of techniques, including MARTI, which is a biometeorological card to examine mean radiant temperature, thermocouples at 2 meters height, and then a radiometer to measure the surface temperature. And we also measured reflectivity over the course of 7 months to see how the pavement actually lasted with respect to the harsh conditions that we see during the summer. And this slide just sort of shows you that we did experience similar climatic conditions when all the field measurements were conducted. So there were 3 neighborhoods that were selected across the city that had the cool pavement installed and which we were able to collect the data. And what this graph is depicting here is actually the surface temperature. And so this was one of the key findings, was that surface temperatures are significantly cooler on the cool reflective pavements relative to traditional asphalts, which is really important when we're thinking about the longevity of the roadways themselves. This actually leads to the roadways lasting longer when you apply that the coating to the top of it, because temperatures ultimately degrade the product when you have the fluctuation between extreme heat during the summer and then our relatively milder winters. However, mean radiant temperature, as we can see here, on the left-hand side is the sidewalk. So those are measurements taken on the sidewalk. On the right-hand side is the street. And the sidewalk, there was no statistically significant difference between the 2 different neighborhoods. However, on the street, so right in the middle of the street, there was a statistically significant difference in which the reflective coatings actually had higher mean radiant temperatures. And we did notice, as one might expect, that reflectivity did degrade over time. So there was about a loss of 10% from the starting point of reflectivity over the course of 7 months. But we were able to notice that when we had rain or street cleaning, which happens sparingly in the summertime, that actually was able to bump up the reflectivity again. So that's a little bit of helpful information for city planners. But something that was a little bit more inconclusive was 2-meter air temperature. So these were 2 separate car transects, and there was not really a statistically significant difference in air temperatures as what we might have expected. It was about 0.2 degrees Celsius cooler was all we really saw. And so I am running a little bit short on time here, but what we did is we followed up the temperature measurements at 1 height and essentially devised a thermocouple array at half-meter increments, so starting with a half-meter up to 2-meter height, to see whether or not that had a difference, told a different story relative to what we were seeing, which is the 1 height at 2 meters. And we did measurements at both stationary as well as transects on the bike within a neighborhood following up in the year 2022, so 2 years later. And what we noticed again was actually a smaller difference in air temperature. So across all heights, there was only a difference of about 0.1 degree Celsius, and none of the differences were statistically significant. This graph just depicts the transects. However, the findings were the same with the stationary measurements. And so what this tells us is that the scale of intervention might not be large enough when thinking about the reflective pavement. As I alluded to before, they have ramped up the program, but if we're just comparing the conditions in one neighborhood relative to the size of Phoenix, thinking about advection and thinking about the surrounding environment, it might not be enough to actually tell us what the reflective pavement would do at a larger scale. There's also a lack of control within the neighborhoods themselves for variations in yards. So thinking about xeriscaping versus trees in the different shade cover, as well as the product itself. So certain cars might leave marks on the pavement, things of that nature. But then there's also uncertainty with the sensors. So if we're only thinking about a difference of maybe 0.5 degree Celsius, there's some follow-up work that needs to be done with the sensors themselves to ensure that we're getting as accurate of readings as possible, because we know from follow-up research that the difference of only about 0.5 degree Celsius can mean millions of dollars in terms of energy savings for when you think about citywide in a city like Phoenix. And so some conclusions more broadly is that when implementing reflective pavement, urban location matters a lot, the background climate type matters a lot, and exposure metric of interest matters a lot. And so mean radiant temperature is a big concern thinking about the social justice implications of this. Sure, many of us might not find ourselves walking in the middle of a street when we have a sidewalk to walk on, but as I alluded to before, urban landscapes are not built the same. And so South Phoenix is actually a lot of locations where there aren't sidewalks. And so for it to implement something like reflective pavement in those neighborhoods, that could be detrimental to the health of people who have no other option but to walk on the roadways to get to where they need to go. And that brings us to sort of the guidance behind the installation of reflective pavements. Is there really is no substitute for shade when considering the health and the thermal comfort of human beings. However, that is actually diametrically opposed to when we think about using reflective pavements. They work their best when they're implemented in low to mid-rise open spaces that allow the sunlight to hit them, because if there's not sunlight hitting them, they aren't doing their job. And so again, it kind of comes down to there is no panacea when thinking about how we're going to mitigate temperatures, and it really matters what your end goal is, whether that is to reduce the cost for city taxpayers or for an individual and their electricity bill and water usage, or if that's for thermal comfort for individuals. And so it's sort of a mix and match when debating where we need to install things and how we're going to implement them. And just the last thing is that we definitely need more clarification on the air temperature, as we expected to see a difference that was not there. But again, you can only mitigate for wind and different climate variances so much as we are trying to get real life measurements. And then also thinking about the human health implications of mean radiant temperature if we are going to install this type of mitigation strategy. And with that, just thank our supporters of the project, and we'll take any questions.
Thank you, Zach, for this interesting talk.